we're going to take a look at how to solve linear systems by graphing. First thing I want to review is what is a line. And if you remember that a line is a visual representation of all possible solutions of the equation, well, what that means is that any xy point on this line will make your equation true. Anything, whether it's a decimal, whether it's crossing at a corner, but any xy point makes your equation true. So then we want to look at, well, what is a system? And a system, it's a group of interacting things. So if you think about your respiratory system, it's the system that allows you to breathe. It's many, many different things interacting that allows you to breathe. Well, for us, in math, we're going to be looking at a system of linear equations today. So what we're going to be doing is we are going to have linear equations, so we're going to have lines that are interacting with each other. And what we're going to be looking at is problems that have more than one equation involved. So right here, this is an example of what a system of two equations are. And the reason I know it's two equations is because I have two lines. And remember, a line is a visual representation of our equation. Now, think about what a solution is. If I were to just have an equation and asked you for the solution, well, a solution is anything that makes it true. So if I look at my first line here, and I said, well, where would the solutions be for this equation, for the equation represented by this line, you could pick anything on this line, any point at all, because anything on this line is a solution. If we were talking about the second equation here, you could pick anything on this line for that equation. So now, with that in mind, where do you think the solution to a system would be? Well, if we're talking about a system, the solution for a system means it has to make everything in that system true. Well, the only place where we have both equations being true is right here where they intersect, where they cross. And the reason that is because if I pick this point right here, well, sure, that's a solution for my second line here, but it's not a solution for my first line. So the only place for this example that we would have a solution for the system, so a solution for both equations at the exact same time, is right here where they cross. So what we're going to do is we're going to look at, well, how do we find a solution to a system using graphing? And the good news is that all this is fundamental graphing slope-intercept form. So for this one, I'm going to start down here at -4, plot my intercept, and then I'm going to go up 2 over 1 to get my equation of my line. Now, when you're doing a system of equations by graphing, you have got to be very, very careful about drawing your lines. They need to be very accurate. So you have got to use graph paper, and you want to make sure that your lines are accurate. So I've got my first line graphed. Now I'm going to go ahead and take a look at my second line. It's in slope-intercept form, so I need to go up here to +1, and then my slope is -3. And I can go ahead and graph that now. Once I get my second line on there, what I'm going to do is I'm going to look for their point of intersection. That occurs right here. Now, they actually occur right on a corner, which is great for us, so we can give the actual coordinates of our solution. And to get to this point right here, we have to go over 1, and then we have to go down 2. So 1, -2 would be the solution of our system. You can always check if your answer is right, because what we're going to do is we're going to plug this in. Our first equation is y equals 2x minus 4. Well, I'm going to plug in the 1 for my x, and I'm going to put the -2 in for my y, and I'm going to see if it's true. So when I solve this out, I get -2 is equal to -2. So it works in the first equation. Now, just because it works in the first equation does not mean that it works in the second equation, because all that tells us is that this dot was definitely on my green line. What we have to do is we have to make sure that that dot is also on the blue line. So we have to check the second equation also. So we're going to plug that solution in again. So we would have -3 times 1 plus 1, and hopefully that'll give us -2. And you end up getting -2 is equal to -2, which it works. So our solution is indeed 1, -2. You always want to make sure that you check your answer, because if you come over here and you graph this wrong, maybe you started at -1 instead of +1, it's going to throw off where your graphs intersect. But you can always check it algebraically to see if it's right. Okay, here's another one that we're going to do. So I'm going to go ahead and I'm going to graph both of these lines. The top one is in slope-intercept form, the bottom one's in standard form. So on the top one I'm going to come down to -2, then do a slope of a +3, and sketch my line in there. My second equation here, that is in standard form, so I'm going to plug in a 0 for my y, solve this out for my x, and I get x to be equal to -2. So I have the point -2, 0 is my x-intercept. And then I'm going to put a 0 in for my x, and I'm going to solve it out for y, and I get 6. So 0, 6 is my y-intercept. And there I have my second line. Okay, now with these two lines, they don't cross on my graph. Well, what I have to think about is, well, will they cross somewhere up here and I just can't see it, or will they cross somewhere down here and I just can't see it? Or are they parallel? Because parallel lines don't ever cross. The only way to find out for sure is to find the slope of each line. Well, the slope of my first line is 3 because it's in slope-intercept form, so I can just pull it right off the equation. The slope of my second line I can calculate. I'm going to do 6 minus 0 over 0 minus a -2. Turns out to be 6 over 2, which reduces down to 3. So notice I got the same slope, so it does turn out that these two are parallel. And if you think about what parallel lines mean, it means they're never going to intersect, which means they're never going to cross, they're never going to have a point in common. So when this happens, we end up with a no solution, because they won't ever touch each other if they're parallel. Now if these were off just a little bit, let's say when I calculated the slope here it turned out to be 2, that just means we need to go farther on our graph to find where they intersect. Alright, here's a third one. So I'm going to graph both of these. The top one is in slope-intercept form again. So go down to my y-intercept of -4, then do my slope of a +2. And I will go ahead and get my line there. Then my second equation, that's in standard form. And with standard form, I want to plug in a 0 for my y. And when I solve this out, I'm going to get x is equal to +2, so I have the point 2, 0. And then put 0 in for my x, and when I solve that out, I get -4, so I have the point 0, -4. And if you look at this, my lines are right on top of each other. These are called coinciding lines. What has happened is I have two very different looking equations that result in the exact same line. So if you think about how many times these lines intersect, they intersect everywhere. Any point you can pull off of the one line will be a point on the other line because they're the same line. So when that happens, we have infinitely many solutions. There isn't just one solution, there's an infinite number of solutions. Now if they ask you to find a solution, you could pick anything on this line. You could have picked the point 2, 0. You could have picked the point 1, -2. Anything on this line will be a solution. But the reason we don't indicate just one is because there's an infinite number of solutions. Anything here will work. So what I want you to do is I've got two different systems here. I want you to go ahead and pause the video and find the solution for system 1, and then go ahead and find the solution for system 2. Alright, on this one I graphed my first line in red, my second one in green, found that they crossed right here at 1, -1. Then I wanted to check it, so I plugged in my values into the first set of equations. Turned out that it worked, so then I plugged my xy values into the second equation. Turned out that one worked, so I can be confident that 1, -1 is indeed my solution. On the second system, I graphed my first line in purple, and then I graphed my second line in green, and they ended up being right on top of each other, which tells me that they've got an infinite number of points in common. These lines coincide, so there's infinitely many solutions for this second system.